Our second type of error is called a random error. And the reason why we know that random errors even exist is because we make repeated measurements, and when we make repeated measurements, what we typically will find is that they'll fluctuate or they'll vary. They don't give me the same reading all the time. If I took the thermometer, very precise thermometer, and I had 5 cups of water, I might measure a slightly different temperature for each one of those cups. And it may not be have anything to do with me or my fault. They may actually, according to that device, give those readings. The fact of the matter is, though, as we said, there is no observer that is perfect, and so it's perfectly normal for there to be random errors. In fact, it would be very unusual for there not to be random errors, because we know as a scientist that there's always some small amount of error in our experiments. Now, one of the things that we can do, though, to reduce random error is that if we make repeated measurements and then average the results, what we end up finding out is that an individual measurement has an error, and it may be a substantial amount of error that would cause it to be much over or much below the real value. But if we take the average, it's likely to pull us somewhere in towards the center where the real answer is probably at. Now, by contrast, the reading error cannot be improved by making repeated measurements. So the reading error that we talked about with the different digital and analog devices, that cannot be reduced. That's simply a product of the device that you're measuring with. It also does depend a little bit on the person using the device, but ultimately it's essentially the device that limits you, that results in this reading error. The random error is something that oftentimes just simply cannot be helped. The same person making the same measurement 5, 10 times in a row will oftentimes find a slightly different number. And you'll find as we go through the experiments that it's very easy to find those situations, especially challenging experiments where it's difficult to make the measurements. It's very likely that making the same measurement over and over will result in slightly different numbers. So to give you an example of what this looks like, both in terms of the data table and in terms of a graph, we have some measurements, and we might presume that these measurements were the number of milliliters that were captured by a rain gauge. So I might have put some small devices outside, essentially small graduated cylinders, and caught some of the rain, and then read the value. Now these rain gauges could have been very close, maybe inches apart or only a few feet apart. So you would presume that any two devices that close would measure the same amount of rain. But the nature of the device is the little drops either hit the device or they don't hit the device, and it's possible that one of them might collect a few more than another one, and another one be much below what would be considered the average. And so you can see the numbers are fairly close together. I mean, it makes sense that these obviously were devices that were very close to reading the same amount of rainwater that had fallen, but if we take the average of these guys, we find it to be 21.5, and that's obviously below the biggest number, which is 22.3, and well above the smallest number, which is 20.5. So the average, and you'll notice there's lots of numbers that are very close to the 21.5, 21.6, 21.7, even the the 20.9 is fairly close. So the average number being 21.5 is not necessarily the right answer. In fact, I'm not saying that it's not the right answer, but there's no way to know whether it's really the right answer. But it's probably closer to the real answer than picking one of the extreme values, like 22. Every measurement is below 22.3. So it's very unlikely that this one. Similarly, I could eliminate the lowest one, because it's very unlikely, since every other measurement is above it, it's very unlikely that that's the real number. It doesn't mean that it's not. It may very well be. But ideally, the thought is that if you make repeated measurements and you take the average of them, then you'll be able to get closer to the real answer. It's just statistically more likely. What random measurements, or I should say random errors, look like on the data is they show up as scatter. So you can clearly see there's a trend with these data points, is that they form a straight line. But if you notice, none of them are actually on the line. Some of them are touching the line or completely off the line. But the trend is there. It's clear that this data is in an upward trend that's in a straight line, and I see that they are scattered. So random error on a graph is shown to us by the fact that there's scatter. In a data table, the random error is shown to us by the fact that when we make the exact same measurement, we get different numbers. Now, you can reduce it by making repeated measurements and taking the average, but the question is always then, how many measurements do you need to make in order to feel confident that you've gotten enough. And that is, unfortunately for you, something that only the observer can decide. What I would suggest is that the general rule would be that the less that the data varies, the less repeated measurements are necessary. At this point, could I make a few more measurements? Probably could make a few more measurements, but realistically, I would find it very unlikely that if I were to add a couple more measurements, that this average is going to change very dramatically. The numbers are all very close together. There's not a lot of fluctuation. It seems like I'm getting pretty consistent results, a little bit of variance, but pretty consistent. And so it's unlikely that the 21.5 will change. But would 2 more have helped? Probably they would. But you have to draw the limit. Obviously, you have a time requirement for the experiment. You can't spend your entire life collecting millions of the same data. You need to produce some results, so you have to decide. And this is something that the scientist decides. It's completely within the realm of the experiment. If I had found that these numbers were going from 17 up to 25, I'd probably take a lot more measurements, because that's a lot of variation. 17 and 25 is a huge percent difference. So it's something that the observer would decide, and it depends on, number one, how difficult is it to collect the data. If, for example, it takes 10 minutes to collect one of these data points, well, then obviously this is an hour-long experiment. That's a lot of time to spend collecting this one small piece of data. If, on the other hand, I can collect the data in 3 or 4 seconds, then I could easily collect 8 to 10 measurements in a span of only a few minutes and still have lots of time to continue on with different experiments. And so the number of repeated experiments is really based on, as you're collecting the data, you're looking at it. You're giving it kind of a preliminary glance to see how consistent is the data. If the data looks very consistent, you don't need so many. But if the data seems like it's jumping around quite a bit, then you probably want to collect a lot more. Maybe like 8 to 10, maybe even 15 data points. It really just depends on what your data looks like. The last aspect of random errors is that, besides allowing us to get probably closer to the correct answer, the repeated measurements also help us to find data that do not match. Those are referred to as outliers. So outliers are data, for example, if I go back to the graph up here, if one of my next data points was, for example, down here, that would clearly be an outlier. Here I have 10, 15 data points that all show this trend, and then this one that's just completely out of place. It seems more likely that there was some sort of serious error, not just a random error, but a really serious error, something in the way the equipment was not set up correctly that caused this number to be so far out of line, because it just isn't consistent with the rest of the data. Now, you would never know that that data existed, or that this, in the case of the data table, would exist without having repeated measurements. So, for example, if this was my only measurement, and that's all I had to go on, was this one measurement, well, then I would find it very difficult to think that I actually got accurate results from this thing, especially since I know that the real answer is way over here and it shows a linear trend. So this data point being so far out makes it clear that it's something that I should probably just eliminate. This is very common. For example, if we use the volume measurements that I had back here with the rain gauge. So you might imagine you're collecting the data, you're getting very consistent numbers, that's all within about 1 of this average of 21.5. But for example, if you imagine that 7th measurement, so I made this 7th measurement, had been 28.5, what would end up happening is the average would then be 26.3. compared to 21.5 that we got before. Now, does 26.3 really seem that it represents that data? Obviously, no, that's not even close. Every data point is at least 4 milliliters below it, as much as almost 6 millimeters below it. So all of the data being below this measurement, even though it supposedly represents the same one, this is probably an outlier. If we were thinking about the rain gauge, it might be possible that an insect or a bird landed on it and caused more water to fall in. And so it's real easy to have random errors like that. The issue is that you would never know that you had this terrible error in this one measurement if you didn't have all the other measurements to reveal the fact that this one does not follow the pattern that's being set by these. Whether this 26.3 shows up in the middle or the beginning or the end, it's irrelevant. It doesn't matter. This data is very consistent. This one being in there, I would bet that these 6 were probably done correctly and something really went wrong with this 26.3. that would require me to just eliminate it, to just get rid of the data. Now, you don't get rid of data without making a note, without telling the person who's reading your lab report that you eliminated that one because it was an outlier, it wasn't consistent with the rest of the data.